And now the only problem that's left is, given a concentration and a volume, so let's say we have a 0.25 molar solution of HCl, and we added 37.5 milliliters of HCl. What number of moles was that? How much actual HCl did we throw in there? Well, molarity equals moles over volume. So moles equals molarity times volume. So 0.25 moles per liter of HCl times 0.0375 liters of HCl. Liters cancels, and we have 0.0094 moles of HCl. So these problems are fairly simple, fairly straightforward. Obviously, to test your understanding, I'm going to throw slightly more complex problems at you. If I'm feeling particularly mean, I might throw very complex problems at you. I'll try not to, maybe. But that's really all there is to it. Let's move on to dilutions. Dilutions happen all the time. You usually prepare what's known as a stock solution, a high concentration of some sort of material, and then you use that to make dilutions that are lower in concentration that are easier to work with. So what happens when you dilute something? Here is your solution, and pour it into a bigger container, and you add water. So what changes from one to the other? Well, you go from a small volume to a big volume. But your moles don't change. They are exactly the same. So if you have this in here, then you have the same amount spread throughout a larger volume. So the number of moles stays the same. So the initial number of moles equals the final number of moles. And what you just saw was that number of moles is equal to concentration times volume. Concentration. Concentration and volume. So as you increase the volume, the concentration is going to go down. Twice the volume, half the concentration. 4 times the volume, 1/4 the concentration. 1 million times the volume, 1/1,000,000th the concentration. So let's say we take, our 0.25 solution, or quarter molar, 0.25 molar solution of HCl. We pull out 100 mils, and we dilute it to 250 mils. Well, M1V1 equals M2 V2. The number of moles doesn't change. The volume and the concentration do. We know the initial concentration. We know the initial concentration. We know the initial volume, and we know the final volume. What we're looking for is the final concentration. So M2 equals M1V1 over V2. Now here's something that might make you happy. This is one of those situations where the units on volume don't matter. Because 0.25 molar times 100 mils divided by 250 mils. The units are the same, so they cancel out. means that our final concentration is going to be 0.10 molar HCl. So that is one thing you can look at for a dilution. But we don't usually say, okay, we add this much solution, what's our new concentration? Usually we're trying to hit a target concentration. Put it another way, if you start with a 1.00 molar solution of HCl, be very careful. If you go from 10 mils, what's the final volume you need to get to in order to produce a solution with 0.200 molar concentration? That is to say, when you dilute something, you're usually trying to get to a final concentration. So, M1V1 equals M2V2. We know the initial volume and concentration. We know the final concentration. We're looking for the final volume. So final volume equals M1V1 over M2. Once again, the units don't matter so long as they match. That's something I should have specified earlier, and I want to stress it now. The units don't matter so long as they're the same for this particular kind of problem. So, M1 is 1.00 molar. The initial volume is 10 mils. The final concentration is 0.200 molar, which means our final volume is going to be 50 milliliters. So once you're done diluting it, you're going to have 50 mils of a 0.2 molar solution of hydrochloric acid. How much water do you have to add? If you're going from 10 to 50, you need 40 mils of water. Let's think about stoichiometry, or solution stoichiometry, I should say. If you dissolve sodium sulfate in solution and get a 0.35 molar solution of sodium sulfate, what is the concentration of ions in your solution? That's what this entire slide deals with. Okay. Up here at the top, we have the balanced chemical equation for the dissolution and dissociation of sodium sulfate. 1 unit of sodium sulfate will produce 2 sodium ions and 1 sulfate ion. So it produces 3 ions in solution. So if you have a 0.35 molar sodium sulfate solution, sodium is an alkali metal, nicely soluble in water, so it's going to go completely to ionization. So 0.35 molar sodium sulfate is actually 1.05 molar ion solution. You could also say that it is 0.7 molar sodium or 0.35 molar sulfate. What I'm trying to really point out here is that when you're working with ionic compounds in solution, you have to keep in mind that the concentration of the substance is not the same thing as the concentration of the ions that it breaks up into. If your salt produces multiple ions, then you're going to get multiples. So sodium sulfate produces 2 sodiums. Hydrochloric acid produces 1 hydrogen, but sulfuric acid can produce 2 hydrogens. And that's the sort of thing you need to keep in mind for your stoichiometry. It's just that I've noticed that sometimes people can be particularly susceptible to forgetting that when dealing with dissolved substances. Because when we move back and forth between the fully balanced equation and the net ionic equation, sometimes we lose sight of the coefficients and where these ions and so on are coming from. And that's important. We need to keep track of that. So let's talk a little bit about different laboratory techniques. Spectroscopy is a really popular one. I'm specifically going to be talking about the different kinds of light spectroscopy, but there are other kinds. Mass spectroscopy, for example, is one that you saw earlier when you did Lab 2. Instead of looking at light in versus light out of a sample, you looked at the actual masses that were being measured. You were looking at the spectrum of masses produced by particle fragments. Well, this kind of spectroscopy, just spectroscopy in general, you shine a light through a sample and you measure the light that comes out. And that gives you a spectrum, either an absorption, typically an absorption spectrum, but you can also get other kinds of spectra. You can get a fluorescence spectrum or a phosphorescence spectrum, depending on what you're hitting the sample with. But all you're doing is measuring the amount of light in versus the amount of light out. So when you look at it, here is the actual setup. Over here you have your light bulb sending out light. The light goes through your sample. Some of it gets absorbed. So you lose some of your light. And then some light comes back out, obviously less light. And here is your detector. That is an eyeball. So you have light coming from your light bulb to your sample, and then you have light coming out of your sample. I here stands for intensity. How intense is that light? How bright is that light? And you can look at different things. You can look at intensity versus wavelength is one thing you can look at. And you can see a spectrum or a chart like that, where here you have a peak showing that it didn't absorb much light there, but it did absorb. No, absorb, yes, absorb. Okay. Because different substances will absorb different amounts at different wavelengths. So this is actually typical of pretty much anything. It will absorb strongly in one spot, not so strongly in another, just depending on what the compound is. So that's one thing you can do. You can look at the absorption spectrum, the wavelengths, to find out what substance it is. And every substance will more or less have a fingerprint, an absorption fingerprint. But another thing you can do is you can look at absorption versus concentration of your substance. So over here, if your concentration is 0, obviously your absorption is going to be 0. Okay, no substance, no absorption. So absorption starts at 0 for 0 concentration. But as you increase the concentration, absorbance will increase as well. It'll start to get kind of weird at very high concentrations. But so long as you're down in low concentration, you'll get a nice linear relationship, meaning that you can use a spectrometer to determine concentration. If you prepare several samples whose concentrations you know and measure the absorbance at those concentrations, then you can get this particular curve. And then you can take a sample whose concentration you don't know, compare it to that curve, and find the concentration. So spectroscopy can be used in a lot of different ways. You can use it to, like I said, find out what substance you're dealing with by looking for the fingerprint. You can find out what the concentration of the substance is by measuring the absorption, or the absorbance. You can also use it to track an ongoing chemical reaction. Because what you can do is, if you have A plus B going to C plus D, then you find a place where one of these guys absorbs very strongly and the others don't. And you track absorbance over time, and you'll see in this case, if D is absorbing, then if you have absorbance versus time, because D is being produced, you'll see absorbance go up and then level off as the reaction slows down. So you can do a lot of different things if you're creative with your spectroscope. And that's where we'll call it quits for this video. When we come back, we'll start looking into pH and the wonderful world of titration.